This video will talk about how the relative permeability of porous materials varies with the wettability. And then we'll use that and the relation to the type of displacement process to make some assessment in terms of recovery or storage applications. But let us start with relative permeability itself, and I'm going to look at three different conditions. The first one is a water-wet medium. So phase one is the wetting phase. We can also call this hydrophilic, right? Likes water. Okay, that will be the first case. The second case we're going to look at is a mixed wet medium, which means that the surface is both hydrophilic and hydrophobic, and there is a mixture of wettabilities. And then the third case we're going to look at is hydrophobic, or oil wet, if we're looking at an oil water system, but you can have hydrophobic materials that are actually gas wetting. They repel water, and in fact gas can be the wetting phase, and we can also see oil as the wetting phase in oil reservoirs where crude oil has essentially coated the solid surfaces, as we've discussed in previous videos. So this will be called oil wet or hydrophobic, depending on your application. Okay, hydrophobic is normally used if we're looking at a gas water system. Oil wet is universally used if we're looking at an oil water system. So I'm going to draw three relative permeability functions. I'm going to look at their typical values, and then I'm going to relate that, as I said, to the type of process and what it means in terms of recovery. Okay, so I'm going to draw three relative permeability functions, as I've already promised. So I'll try and use the whole board, and I'll try and keep to a similar scale, so we can do this for comparison purposes. So these are the axes. Okay, so the axis here is relative permeability. One is going to be at the top, 0 here. This is the saturation of phase one, again a 0 and a 1. Hopefully I don't need to label all the time. This is all relative permeability. I haven't changed anything here. Saturation of phase one, this is the 1, the 0, the 1, S1, and a 1 here. Okay. So these are my axes. Now I'm going to draw the functions. Now, we've already done the water wet case in the previous video, so I'm not going to dwell on it, but let's just go through it again because it's good for revision, and this is really key for the quantification of multi-phase flow in porous media. I'm going to actually take a case with really quite a high residual oil saturation. Here, 35-40%. Okay, and we have a water relative permeability that does this, and an oil or a gas relative permeability that, as I said, goes here. And you see now the crossover point is very close to the residual. So this is the initial saturation. This is your residual saturation, and that's normally, as I said, somewhere between 0.5 or 0.2. The maximum relative permeability is typically in the range of 5 to 20%, and here KRO max is typically 80% or greater. Obviously, you can't keep going greater than 1, but that's for the water wet case. And we've already seen that. There should be nothing new. Don't get upset if it's very slightly different from the previous function I did. Of course, different porous media have very different pore structures, and of course that can be different depending also on the initial condition. In the other cases I'm going to look at, I'm going to assume that the initial water saturation is the same in all cases. Now, there is an argument that says if you're more hydrophobic materials tend to have, particularly if you're looking at oil applications, tend to have a lower initial saturation because basically you've pushed the oil right onto the surfaces at a high capillary pressure. That's fine, but in this case, just for comparative purposes, we're going to assume this is the same. And this means the initial condition is going to be the same as well. So in the three cases here, I'm going to start essentially with the same relative permeability phase 2. Okay. The other thing I want to say here is that we see this rather low wetting phase 1 relative permeability, and that's because it's a percolation displacement. So this is percolation. It's a percolation-like, and I'm going to talk about that a little bit later. Okay, percolation-like, and of course we're just seeing trapping as well. We're seeing significant amounts of trapping of the non-wetting phase. So these are the 2 points I want to emphasize. Okay. Now let's look at the hydrophobic case, the sort of opposite case. Now the opposite case here is now where phase 2, the oil or the gas, is the the oil or the gas is the wetting phase. The water, phase 1, that I'm injecting, is the non-wetting phase. Okay? And in this case, the displacement process is rather similar to the primary drainage process that I've described in previous videos. What's happening is the water now, as the non-wetting phase, okay, is advancing through the pore space in an invasion percolation-like pattern. That is, it goes through the widest throat, then it will fill the pore. It's non-wetting, doesn't like the surface, stays away from the surface, goes in the big pores. Okay, so it goes through the widest throats, then the big pores, then the next widest throat, and so on, in a connected pathway through the pore space. And what happens, certainly from a percolation perspective, it is at low saturation, it connects across, going through the largest regions of the pore space, and then obviously provides further connections. So what we see here is that the relative permeability of phase 1, the non-wetting phase, rises actually really quite rapidly. And when we get to near the end of the displacement, it's basically filling all of the larger pore spaces. So you'd expect a bit like this to have actually quite a high relative permeability value. So we normally end up with quite a high relative permeability value and a relative permeability that does rise really quite steeply like this. And it doesn't necessarily have to get all the way to here. All right, let's say here, you normally find that the maximum relative permeability of phase 1, the non-wetting phase now, right, is typically greater than about 0.4, 0.5. Now, what about here? We look here, how much is actually trapped? Now, if you recall one of the previous videos, I talked about what would happen in a hydrophobic or oil-wet porous medium. And I explained that the water, phase 1, goes into the center of the pore space, but there's still phase 1 that remains in the corners after primary drainage. In between, you have a layer of oil or a layer of gas that is sandwiched in the pore space, squeezed between the water in the centers and the water in the corners. And what those layers do, although they don't provide much flow because they're thin, they do provide connectivity. So in fact, in a strongly hydrophobic medium, the other phase, phase 2, is wetting. And that means that it's not really trapped. Just in the same way as here, if it's strongly water wet, the water is always in the corners and it's actually difficult to really get trapped. You can push down to quite a low saturation. So the residual saturation here is relatively low. Okay? So what we see in terms of the relative permeability of phase 2 is something that looks like this, and I'm going to explain why. So this is the residual saturation, S2R, and that's typically less than about 20%. Sometimes it can be 10% or even lower than that. Okay. And what you see here is a very rapid drop in the relative permeability. Okay. Now why is that? Well, surely it's obvious. The phase 1 goes through the big pores, the major junctions, the wide streets. So obviously, for the other phase, for whom those are blocked off, that really decreases the conductance very rapidly, basically chosen all the places where there'd be most flow, the biggest elements, and you've blocked them off. And this is really quite extreme, because if you think about it, when I talked about quantifying conductance, I said how conductance goes as area squared, radius to the power 4. And don't get hung up by the fact, oh, that was only for a circular tube. I'm sure if it's something different, it's going to be different. Yeah, there's going to be a different coefficient. You know, it's not pi by 8. It's going to be something else. But the area squared stays the same. It's always the same. That's the physics. So if you have an element of radius r and you have another element of radius 2r, there's a 16-fold difference in how much flow you have in it, regardless of the shape. It could be whatever shape you like. There'll be some coefficient, but the scaling is the same. So you start breaking off connections through absolutely the most conductive areas, and the pore size distribution normally spans a couple of orders of magnitude. So you're looking at enormous differences in flow potential. So the flow decreases rapidly. Then you see this region where the relative permeability is close to zero. It's not exactly zero. Well, why is that? Because the only flow is through layers. And the layer conductance goes as, guess what? Yeah, area squared. But they're little thin micron scale layers. So they have much less conductance, much less conductance than the other pores. So here we see characteristically this region where the relative permeability is close to zero, and that we call this the layer drainage. You might say, why drainage? Well, actually, this is a drainage type displacement, isn't it? Phase 1, which we're injecting, is the non-wetting phase. That's a drainage type displacement. So this is layer drainage. You see this. The maximum relative permeability, as I say, is much the same, but we see this sharp drop here. Sharp drop. And a sharp rise here. Rapid rise, okay? And in terms of the physics of the displacement, this is invasion percolation. And there's little trapping. I mean, there is some trapping because these layers do eventually, basically, they break, so they're not there. You don't get down to a zero residual saturation, but it's very low. So there's little trapping. Okay. Now, those are the two extremes. Now let's think about them in terms of sort of recovery, particularly, and this is particularly relevant for oil field applications where it's easiest, but it's also true if you've got a gas retained within the pore space. As shown here, when we described this before, you basically start at this initial saturation and very rapidly you essentially get to the residual saturation. So if you have a strongly wetting phase and it's injected through a porous medium, you're going to find that you leave behind that residual saturation, more or less straight away. You inject the water, as soon as the water has gone through the porous medium, you're leaving behind that residual saturation. Now, what about a hydrophobic medium? What actually happens is you inject the water through the phase 1 through your porous medium. At a very low saturation here, the water flows more readily than either the oil or gas that's retained in the pore space. So although theoretically you can drive the system down to a low residual saturation, you can only do this by injecting lots and lots and lots and lots of water. So in the lab, you can set up a pump and you can be injecting water for months. And the reason is because here, to get 1 cubic centimetre of oil or gas out, you need to be injecting thousands, if not hundreds of thousands of cubic centimetres of water. So you're injecting a lot of water and a little bit of oil or gas is coming sort of dribbling out. So if you think about this in terms of oil recovery, you can't inject an infinite amount of water. It doesn't make any sense economically. You normally inject enough water to basically fill the pore space once. And so what happens is you have to abandon your field at a sort of saturation around here, because you can't drive it to here, because this would involve much more flow of water than it is of the oil you wish to recover. So in fact, in terms of recovery, a hydrophobic material basically retains the wetting phase, the oil or gas, within the pore structure. And it's very difficult to remove it from the pore structure. Even though it's technically not completely trapped, it can flow. So sometimes people get, the residual's low, so you're going to get it all out. Yeah, I'm going to get it all out. In theory, if I keep pumping and pumping and pumping and pumping and pumping for months, okay? In theory. But in practice, if I'm just going to inject a little bit of water or hope that it sort of pushes its way out, I'm going to actually retain a lot of phase 2 because it's the wetting phase. It likes the surface. It likes being in the porous medium. It doesn't like coming out, okay? Okay, so that's those two extremes. This actually, you get trapping, but in terms of recovery, actually isn't too bad because at least you get down to the residual saturation. This, in terms of recovery, certainly for oil recovery, is very bad, actually, because you inject the water goes through all the large pores, it gets connected, it flows readily, and you retain a lot of the oil in the pore space. And that can be done rigorously, quantitatively with the mathematics. I'm just explaining it sort of qualitatively, but it's entirely consistent with the physics of the displacement. Okay, you might say, well, that's all fine. So the mixed wet case is something in between. Now, until recently, that's exactly what people thought. They thought, yeah, mixed wet, this is one extreme, this is the other, it's in between. Well, it's not quite. So let's go through the things that are in between and then the things that are not. So the first thing is the residual saturation. This actually is in between because you can get snap off and you can trap some of the what is a non-wetting phase in the water wet, in the phase 1 wet regions of the pore space. So in those regions of the pore space, you can get some trapping, but you can also get layers. So there will be more trapping. So this is your residual saturation, S2R, and your residual saturation is typically somewhere between 0.2 and 0.1, typically, right? So there's a bit of an overlap here, right? But this could definitely be a lot lower, so you can't really just look at the residual, but it tends to be certainly greater than 10%. So S2R, so 0.1. Okay, something like that. Okay, so that's your residual saturation. In terms of the relative permeability of phase 2, so this will be the oil or the gas, you're going to see a rapid drop. All right, maybe make that look a little bit smaller. Right, let's do that. You see a rapid drop, something like that, and you still see this oil layer drainage regime. So what we are seeing here is the filling of the water wet regions. There's still going to be a decrease in relative permeability. You see this even if it's a water wet case, and then you move on to filling the oil wet regions or the hydrophobic regions of the pore space. You still see this layer drainage regime, maybe not over such an extensive range because there are not so many hydrophobic regions of the pore space, but you still see the relative permeability heads to 0, sort of like this. Okay, so this is layer drainage as well. So if you look at the relative permeability of phase 2, okay, there's slightly more trapping, there's slightly less of this. It's really very difficult just to judge from the functions what the wettability is. Turns out, so this is intermediate, okay? The amount of trapping is intermediate. It doesn't necessarily decrease so rapidly here as here because now it's filling some water wet regions to begin with, you know. So it's somewhere in between in terms of the relative permeability at phase 2. Fair enough, nothing controversial there. What is different is the relative permeability of phase 1, okay, the water relative permeability. So I'm going to draw it. Right. Its maximum value, again, is uncontroversial. KL1 max is typically in the region of about 0.4 to 0.2. So it's intermediate between this extreme, and this extreme, and that makes total sense, doesn't it? Because in the water wet regions, you've actually filled the smallest regions and you've had some trapping. In the hydrophobic, in the oil wet regions, okay, it's a bit more like this, so it's somewhere in between, and some of the flow paths are blocked. So this endpoint, again, is between the water wet and the oil wet or the hydrophobic extreme, is not a surprise. So nothing to see there, nothing really to see here. The feature which is unique to mixed wettability is here. So the two features here are a very, very low relative permeability of phase 1, and by that, not somewhere intermediate, actually below what you'd see in a water-wet medium, okay? Below. Then you see a very rapid rise near the endpoint. You see an almost sort of vertical type relative permeability. Something shoots up. Now, I'm going to talk a little bit more about this in this video, but while I've got these functions on the board, I'll just remind you of one of the things we said about mixed wet media. We said actually that the displacement was percolation-like. We didn't say it was invasion percolation, we said it was percolation-like. We said that what you do is you invade the water-wet regions everywhere, and then those are sites which nucleate the filling of the hydrophobic regions. So it's percolation-like, then what that means is you're only going to get real flow once phase 1 is connected through the centres of the pore space. So this is why you see very low and it goes up. You might say, yeah, well, why do you see that with water then? Difference is if it's strongly water wet, you've also got layer flow. You've got these wetting layers. And as the displacement proceeds, these wetting layers can swell, so they're providing additional conductance, even if the centre of the pore space is filled with the other phase. As I'm going to show in a little bit, that's not the case if you're mixed wet. So in fact, the relative permeability stays much lower and then shoots up, and it looks actually a bit more sort of pure percolation, you know. Nothing's happening. Now I collect, bam. Okay? So that's what we're going to show in a little bit. We've introduced the relative permeability functions, but to understand those a bit more, what I'm going to do is I'm going to just look schematically at the displacement process. Again, this is going to be phase 1 displacing phase 2 under 3 conditions. One is hydrophilic. So phase 1 is the wetting phase. The water is wetting. The other is mixed wet. And the other is hydrophobic or oil wet. So what these points represent is they represent the pores and the connections between them are the throats, and we're going to annotate those. And then under here is a typical cross-section of a pore or throat to look at the configuration of the fluids. So let's look at the hydrophilic medium first. We've already discussed this. This is a percolation type displacement. So when the wetting phase, which I'm going to indicate in this case in blue, moves in, it first of all just fills the narrowest regions of the pore space. Okay? And that's by snap-off. So just by random, imagine that's the narrowest throat. That's what it's going to fill. Then it's going to fill this one, and it's going to fill this one, and it's going to fill this one, then it's going to fill this one. But now let's look. Imagine there is a throat here. Okay, I'm sort of putting in dotted lines. I don't want to sort of draw it. And I look at the cross-section. Okay. So this is that throat or pore, any region of the pore space in cross-section. What we have initially at the end of primary drainage is this is the wetting phase that's right in the corners of the pore space, right? The non-wetting phase has been applied at high pressure at the end of primary drainage. The water is confined, the wetting phase, phase 1, the water is confined to the narrow regions right inside the corners. But now, as I'm filling more of the pore space, I'm dropping the capillary pressure. I'm increasing the pressure in phase 1. And what this means, that even in an element that has not been filled, the layers get thicker. And indeed, that's how snap-off occurs. How does snap-off occur? It's because these layers get so thick that the two menisci meet and it's no longer stable. So obviously the layers get thick. And of course, in a throat that is just about to have snap-off, these layers are really quite thick indeed. They're occupying really a significant fraction of the area. So if this is a throat about to snap off, although it's got, yes, phase 2, I can label here phase 2, the non-wetting phase in the centre of the pore, phase 1 has a reasonable conductance, right? It's not negligible. So that's the reason why the water relative permeability, the relative permeability phase 1, in a hydrophilic medium, okay, it is low, it is in the smaller regions of the pore space, but it is increasing, it is getting going because you're able to swell these layers, even if the regions where the centres of the pore space are filled do not connect. Now, of course, eventually they do, right? So imagine this is a percolation type process. Imagine I do snap off here and then it wants to fill here. Okay, you fill here, right? So you do some pore filling. We talked about this. Oh yeah, this will be an I1 event, so that's quite favourable. So we'll have pore filling here. Maybe this connects and this pore fills and then the throats. And now we're connected across the system. Okay, and then eventually we'll also get some trapping. Okay, so you can imagine a case where there's a pore here, right? But then the next event is a snap off, say like that. And so that pore is trapped. Okay, so we can get trapping, we can get pore filling. Okay, there are a number of complex processes, but fundamentally the thing here is it's percolation. Let's say that again. And we do get trapping. So this is percolation with trapping. Okay, now let's look at the other extreme, the hydrophobic case. So what happens here? Well, initially, exactly the same thing, right? Any pore, throat and cross-section has the water right in the corners. That's phase 1, right in the corners of the pore space. Okay, but now what happens is there are no water-wet regions. So in fact, because we've now altered the wettability of the surface, so these surfaces now are hydrophobic, they don't like water. The only way water can move across from the corners is really to bulge out. So instead, what is more favourable when you go through the equations is piston-like advance, basically from the inlet to the outlet. So now, phase 1, I'm not going to just draw in blue, I'm going to draw in this pink colour to show that phase 1 is the non-wetting phase, it's hydrophobic, and we have an invasion percolation process. Okay, so I'm not saying anything that's different from what I said when I had the relative permeabilities, and now what it's going to do is it's going to invade the widest regions of the pore space, so not necessarily what I showed here, so, and then it's always going to fill the pores, right, like spinning the pores, there's never a problem there, okay, and so it has an invasion percolation type process, okay, like this, and like this. And what do I mean by an invasion percolation process in terms of, okay, so now, if I look at now an element, say here, where phase 1 hasn't been, what does it look like? Well, I've drawn phase 1 as blue, but I'm drawing it as pink here, so let's not try and be too confusing here. Okay, what we see here is phase 1 is at a higher pressure than phase 2. The capillary pressure is negative. I'm having to push phase 1 in, I'm having to push the water in. And so the water is bulging out. But these layers are pinned. Okay, so nothing's happening here. Okay, so there's nothing to see there. There's basically very little conductance in these pinned layers. And that's going to be significant for this case, by the way. Okay, so nothing much is happening here. But on the other hand, phase 1 is connected through the centres of the pores and throats. And these are the largest ones. So the relative permeability, once it gets connected, rips or whacks up. Okay, and that should make sense. In a region of the pore space where phase 1 has been, okay, what's going to happen? Phase 1 enters the centre of the pore space. We've already shown this, so this isn't new. Phase 1 has entered the centre of the pore space like this. Okay, there's the same curvature both sides. Okay, so this is phase 1 now. I'm giving it a pink label so that we don't get confused with the colour scheme. And then phase 2 is confined here, okay, phase 2, which is actually wetting, okay, the defending phase, the water, the oil or the gas phase, sorry, is the defending phase and is a wetting phase, and this is trapped in a layer here, okay, so this is what we have as a layer. So once we fill the majority of the pore space, we can imagine the displacement proceeds, okay, once we fill most of the pore space, then what we have is for phase one, it's filling the centers of the pore space, well connected, high relative permeability. For phase two, right, the oil or gas is now the wetting phase. It's clinging to the surface here because it's wetting, it likes it. It's confined to the narrowest regions of the pore space, and it's just in these layers, and that's that layer drainage regime. Okay, and these layers can become quite thin, typically of order the size micron or less. So hopefully this isn't anything really new. These diagrams I've already shown you, so shouldn't be overly confusing. But now let's do the mixed wet case, because that's really rather more intriguing. In the mixed wet case, maybe what I could do is I'd indicate in blue the filling of the water wet regions. So what happens is you do have layers. Okay, you've got these wetting layers here. Okay, so in the water wet regions of the pore space, it's just as it is for a water wet case, right? You can flow through the layers, and the interesting thing is there is connectivity through the layers, even if this turns out to be a hydrophobic, right? An oil wet pore, there's still a wetting, there's still the phase there, phase one, which was originally a wetting layer. It's no longer a wetting layer, but it's still there, so it still allows flow. So in fact, you can flow anywhere in that network, in this network. So what you're going to do is you're going to do something similar. Imagine that this is the narrowest water wet throat. You're going to fill that, and then maybe that, and then maybe that, and then maybe that. Okay? You're not going to have much pore filling. Pore filling is not favourable, even if it's water wet. So you're going to fill a few throats like this. Okay. Now imagine this is most of the water wet region of the pore space. Maybe you fill a pore, but not necessarily all the throats, because this throat may be a hydrophobic throat, so it's not favourable to fill straight away. So those are the water wet regions of the pore space that you filled. Okay, you might also get some trapping. Okay, so you can imagine a case where this is a pore here, and just by snap off I fill these. Okay, but this is trapping, so you can get something that's trapped. Okay. Now we're going to have to push the water in, push phase one in. The capillary pressure becomes negative. We start filling the hydrophobic regions of the pore space. You know, I say, well, this is just the same as here, it's invasion percolation. Yeah, but actually, not quite. Because imagine you've got a big hydrophobic pore here. There's water here. I could fill it with piston-like advance. I don't have to do this bulging out from the corners, which is very unfavourable because the curvature is very large. The radius of curvature is tiny. I've got here a throat full of water. All I have to do is fill the pore. 2 sigma cos theta over r pore. Okay, it's a negative capillary pressure, but it's only slightly negative. I only need a little bit of push in the water, and I can get the water to fill here. Right. And actually, quite likes filling pores. And we said, well, it can fill the pores of the inlet, maybe. But it's still going to start filling all these other pores. Okay, and maybe it fills a few throats, but it definitely likes filling pores. So we get this sort of arrangement. Now, at this point, the saturation of phase one, which is the combination of both the blue and the pink bits, right? Saturation is quite high. But just a moment, I haven't connected from left to right yet. And what's more is if this is, say, a hydrophobic throat here, what do I have in cross-section? Well, in cross-section now, phase one bulges out into phase two, but this interface is pinned, just as I showed here. It's not moving. So what we're doing is the only way phase one can move is connected across the pore space is through those regions that are filled. But look, we're not really going anywhere because it's blocked, trapped. Okay, we're stuck. So we have to go through these layers here, but these layers are pinned. So their conductance is tiny. So you have these pinned layers, and that basically limits the flow. So the saturation here, the water saturation could be 50%. What's the relative permeability? Almost zero. So in fact, the relative permeability in this picture is lower than it is in this picture, because in this picture, all the layers are nice and fat. In this picture, the saturation could be even higher. There's no connectivity, and the layers are pinned. Now, eventually, what happens is, okay, now I connect in a wide pore, I just have one more connection, and suddenly I'm away, all right? Because now I've got a connection through the pore space with large elements, okay, some of the narrower elements here, but basically, once the hydrophobic regions get going, right, I'm in good shape. I actually fill some of the wider regions. So the relative permeability is almost zero, almost zero, almost zero, almost zero. Then you reach the percolation threshold, you connect, and whack, up goes the relative permeability. So in terms of the shape of the relative permeability functions, this explains why in a mixed wet medium, you actually can have a phase 1 of water relative permeability, an intermediate saturation that actually lies below the water wet case. Okay, below the water wet case. Now, what does that mean in terms of recovery? It actually is very favourable for recovery. It's very favourable for it to allow water, say, to displace oil, because the water is held back until a very high saturation, and there is less trapping. Because although there can be some trapping, remember we've also got now these layers in these regions, and so there is less trapping. So you get the combination of holding back the water plus less trapping can be very favourable for recovery. And that's certainly true of oil recovery. You can actually get most of the oil out of a mixed wet type rock. But you can also see it in electrochemical devices, where you have this fibrous porous medium that's a mix, basically plastic, hydrophobic coating and hydrophilic coating. And what it enables water and gas to move through that fibre really quite efficiently and without much pressure difference between them. And that's very good for the device performance, because you've got a fuel cell, you react hydrogen and oxygen together, you create an electrical circuit, so you're generating electricity, but of course hydrogen and oxygen together for water. So you need the gas to move into the material and the water to move out. And so it's this mixed wet condition that's actually the sweet spot for recovery. So it's both in the subsurface, underground, mixed wet conditions are actually very good for the two phases to displace one another. There's not a lot of trapping, and the water particularly is held back. But you also see it in manufactured settings as well. Okay, so that concludes what I wanted to say very briefly about multi-phase flow in porous media, where you've got two phases and their relative permeability characteristics. The next thing that's coming up is the fascinating subject of three-phase flow, where we have oil, water, and gas all simultaneously present in the pore space.